The second talk of the session is Credible Mechanisms by Mohammad Akbarpour and Shengwu Li. And this is actually the paper that won the Best Paper Award in the conference. So Edith is presenting the award to the author.
Thank you so much.
Very pleased to present the award.
Thank you, it's an honor.
So I have 2 copies, one for both.
Cheers.
All right, with that, let's welcome Shengwu.
Thank you so much. It's an honor to be here. Thank you so much for coming to the talk. So this is joint work with Mohammad, who's right over there, and an amazing co-author and a dear friend. This is a paper we started, I think, arguing about in Berlin a year or 2 ago, where we essentially try to come up with a reasonable definition of what it would mean for an auction to be incentive compatible to the auctioneer. So this starts from the following, I think, quite natural observation. Imagine you're an auctioneer running a second price auction, and you receive 2 bids, B1 and B2, B1's higher. Now, something you could do is you could lie to bidder 1 about bidder 2's bid. You could say that bidder 2's bid was B1 minus epsilon. Now, if you do this, probably bidder 2 doesn't know how much bidder 1 is going to pay. Bidder 1 doesn't know how much bidder 2 bid. So you would thereby increase your profit because neither bidder would notice. Now, this is, of course, not an original observation. Vickery, in the paper that invents the second price auction, points out that the auctioneer might want to do this. Now, imagine you tried to do that same trick in a first price auction. So you're running a first price auction, you get bids B1 and B2. Now, we're playing the separating equilibrium, so what you do is you invert bidder 1's bid to recover his value. You make a take it or leave it offer to bidder 1 of his value minus epsilon. Now, if you do that, probably bidder 1 says, hold on, you're breaking the rules. The rules are that I pay my bid, not that I pay whatever else you decide after I've submitted my bid. So it seems like there's something special about the first price auction. And this is, of course, also, in fact, in Vickery's very prescient paper. Vickery observes that the first price auction is, in some sense, automatically self-policing, whereas the second price auction is not. And our question, in essence, in this paper is which auctions are, in this sense, self-policing? How can we design an auction that is incentive compatible for the auctioneer in the sense that the auctioneer would not want to cheat? And to be clear, this is not just a fairy tale that we've made up for the purpose of this paper. It turns out there are now some quite serious allegations that auctioneers selling ads on the internet using second price auctions might in fact be cheating in the way that I've just outlined. So this is an industry newsletter. The title of the newsletter goes, How SSPs, those are the auctioneers, use deceptive price floors to squeeze ad buyers. And it says, in a second price auction, raising the price floors after the bids come in allows the auctioneer to make extra cash off unsuspecting buyers. And this is the reason that the journalist advances for this happening. He says this practice persists because neither the publisher nor the ad buyer has complete access to all the data involved in the transaction. So in essence, no player in the transaction can know for sure that the auctioneer is breaking the rules. Okay, so that's probably the first big assumption of this paper. The big assumption is that the auctioneer engages in private communication with each bidder. So the auctioneer talks individually to each bidder, but doesn't use public announcements, and the bidders don't talk directly to each other. Now, there are a number of reasons why you might do this. It could be that bidders have an intrinsic desire for privacy. It could be that bidders are worried about strategic aftermarkets and therefore wish to hide how much they value the object. Or it could be that the auctioneer is concerned with preventing collusion. So it's fairly common, for instance, in government spectrum auctions to make it illegal for bidders to directly communicate with each other. But for whatever reason we might advance this, we're just going to impose this as an assumption. In this talk, the auctioneer communicates privately with each bidder, and that is going to permit the auctioneer to misrepresent to each bidder what the other bidders have done. Now, this is the model. There's one object for sale. There's some set of bidders n. There's a finite type space theta I for each bidder, where you'll notice I'm using epsilon to denote the distance between adjacent grid increments. So epsilon is just the grid increment on the type space. There's a set of outcomes X, where an outcome specifies who gets the object and how much is paid. We're dealing with private values, quasi-linear utility for each agent. The auctioneer also needs a utility function. The auctioneer's utility is just revenue. Okay, so for this talk, we're going to represent an auction rule as a game tree. And the reason why we need to do this is it turns out that when the auctioneer can cheat, the revelation principle no longer applies. It can in fact be very dangerous to hand all your information to the auctioneer at once. So you may want, for instance, to tell the blue player a little bit about what the red player has done at the point when he's called to play. You may want to communicate with the red player more than once. These are all features which we can't abstract away. Each terminal node in these game trees specifies an outcome. It tells us who wins and how much they pay. Now, an agent strategy, a bidder strategy in this world is just a function from information sets and types into actions. So it specifies for each information set that the bidder encounters, for each type that he might have, which action he takes. And the object of analysis is a protocol. A protocol consists of an extensive game form G and an agent strategy profile Sn. Where as usual, we're going to require Sn to be a Bayes-Nash equilibrium of the game form G. We're going to add some technical restrictions. We're going to restrict G to be finite, to be non-random, so there aren't chance moves, to have perfect recall. And it turns out that for our purposes, it will be without loss of generality to restrict attention to game trees where every history is on the path of play. That's to say, for every history, there exists some type profile such that at the equilibrium strategy profile, that history is on the path of play. So to ease exposition, I'm just going to remove all the off-path nodes when I'm describing a game form. So here's how the auctioneer can cheat. This is a simple second price auction. The red bidder bids either 10 or 30. The blue bidder, without observing red's action, bids either 20 or 40. The outcomes at the end are just the things that are required by the second price rule. Now imagine you're an auctioneer running this auction. What you do is you pick up the telephone, you call the red bidder. You say, hey, Red, you're up. Do you want to bid 10 or 30? And Red says, OK, I'll bid 10. Then you put down the telephone, you call up blue bidder, and you say, Blue, do you want to bid 20 or 40? And Blue says, OK, I'll bid 40. Now, the rules of the game require at this point that Blue wins and pays 10. But you like profit, so what you do is you instead allocate the object to Blue and charge him 30. Now, why is this OK? Well, the red bidder doesn't know how much Blue is paying. So Red goes, probably, this is what happened. I bid 10, Blue bid 40, and I didn't win. Now the blue bidder, on the other hand, doesn't know how much the red bidder bid. So the blue bidder says, OK, I was called to play, I bid 40, I won, I paid 30. What happened is that red bid 30. So you notice in this case, the auctioneer increases her profit by misrepresenting to the bidders what the other bidders have done. In particular, by misrepresenting red's action to blue, by misrepresenting red's preferences to blue, the auctioneer increases her profits. So we're just going to take this and generalize it to be a bigger game that permits these kinds of cheating from the auctioneer. So here's the bigger game. In step one of this game, the auctioneer chooses a bidder. In step one of this game, the auctioneer either chooses an outcome and ends the game, or goes to step two. In step two of the game, the auctioneer chooses a bidder and sends along some message M along with some set of acceptable replies R. The bidder privately observes this and then chooses a reply. The auctioneer privately observes the reply, and then we go back to step one. Now, of course, you've noticed there is an isomorphism between auctioneer strategies in this game and game trees just for the bidders. In particular, a message is just like an information set. A reply is just like an action. So we can think about the auctioneer having a strategy that runs a particular game form G. That's to say, the auctioneer can start at the initial history of the game form, contact the bidder who's meant to play, send a message that corresponds to the action, allow replies that send a message that corresponds to the information set, allow replies that correspond to the actions, advance the history as the rules require, repeating this process until she hits a terminal history, whereupon she chooses that relevant outcome and ends the game. The full commitment paradigm just says that to run some game form G, the auctioneer commits to S0G. That's to say, a strategy that's unique up to a relabeling that just contacts the bidders and proceeds as the game rules require. We're going to allow the auctioneer to deviate, in particular to deviate to any strategy that an individual bidder cannot distinguish from the rule-following strategy. And here's how we formalize that. So in the course of this messaging game, bidder I observes two things. First, bidder I observes the communication sequence, the messages and responses between himself and the auctioneer. Second, bidder I observes whether or not he wins the object and how much he pays. So I'm going to notice, in particular, that if I fix an auctioneer strategy profile S0, a bidder strategy profile Sn, and a type profile theta n, that results in some unique observation for bidder I. Let's call that OI. So let's suppose that the auctioneer promised ahead of time to run this protocol GSN. We could say that bidder I's observation O prime I has an innocent explanation if it's consistent with the conjecture that the auctioneer played by the rules. That's to say, if there exist types for the other bidders, theta prime I, such that O prime I is produced when the auctioneer plays the rule-following strategy, but the other bidders have those types. We could then say that a deviation, an auctioneer strategy S0 is safe if for every bidder and every type profile, that bidder's observation has an innocent explanation. So these are, in a sense, the patterns of behavior for the auctioneer that can be made to look legal by misrepresenting the preferences of the other bidders. We're then going to say that a protocol is credible if for any safe deviation by the auctioneer, the expected payoff to the auctioneer by following the rules is at least the expected payoff under the safe deviation. So you notice, just as standard incentive compatibility says, no bidder should profit by cheating, where cheating involves behavior that can be made to look legal by misrepresenting his own preferences, credibility says the auctioneer should not profit by cheating, where cheating is behavior that can be made to look legal by misrepresenting the preferences of the other bidders to this bidder. Now, you might ask, is this, are we taking the wrong expectation here? What if the auctioneer encounters new information in the course of running the protocol such that she now wants to deviate given her updated beliefs? Well, of course, in game theory, the auctioneer strategy is a complete contingent plan of action. So there exists an auctioneer strategy that plays by the rules unless she encounters that information and deviates thereafter. So it turns out that even though we've written this as an ex ante expectation, this definition implies that the auctioneer best responds even to her updated beliefs. Cool? So this is, I think, a fairly natural definition to have in hand. Now I'm going to state a bunch of results. I'm going to assume a few things for this talk. Most of these are relaxed in the paper if you have a look at the latest draft. So I'm going to assume that the distributions that the bidder's values are drawn from are independent, symmetric, and regular. Where by regular, I mean that the virtual values are increasing. That object up there is just a discrete version of the regular kind of virtual values that we use all the time. I'm going to assume that only winners make payments. I'm going to assume that there is a fixed tie-breaking order. That's to say, if there are two bidders, I and J, who both have the highest type, the way I break the tie between I and J is always the same. It's some deterministic order on the bidders. Okay, and with all that set up, we can now say, I think, some quite interesting things about the set of optimal auctions. So under these assumptions, there is, okay, so definitions I think we probably all know. An auction is static if each bidder has exactly one information set and is always called to play. An auction is strategy proof, that's to say dominant strategy incentive compatible, if each bidder's assigned strategy is a best response to any opponent strategy profile. So I think it's safe to assume that basically everybody at this conference knows there is a unique static strategy proof optimal auction under the assumptions I've just stated. It's the second price auction. So as epsilon goes to 0, that's to say as the grid for the types becomes arbitrarily fine, a protocol is static and strategy proof if and only if that protocol is a second price auction. This shouldn't surprise any of us. This is essentially implied by the Green-Lafont-Holmstrom theorem. Now, a very natural question is, the argument I gave you just now establishes that second price auctions are not credible. So is there a static, credible, optimal auction? And the first result of this paper is that there is one, and there is essentially only one. So result one is that as epsilon goes to 0, a protocol is static and credible if and only if that protocol is a first price auction. And the way to see this is essentially second price auctions give the auctioneer room to increase her profits by lying about the other bidder's type, because each bidder, the winning bidder's payment depends on what the other bidders have done. In order to make sure that the auction is credible, you essentially need to remove all opportunities for the auctioneer to do so, which is to say that each bidder's payment, if he wins, has to be a function only of his own type and not the other bidder's type. But of course, there's a unique static auction that does that, namely the first price auction, so that's the thing you've got to do. Now, this immediately tells us that restricting attention to static protocols means that we face a trade-off. You can either make it so that the bidders have dominant strategies, or you can make it so that the auctioneer can't profit by secretly cheating, but you can't do both. And a very natural question to ask is, okay, suppose we allowed the auctioneer to do something clever. Suppose the auctioneer could use not just a static protocol, but an arbitrary extensive form mechanism. Could in principle contact bidders more than once. Could in principle ask bidders for only part of their information at a time. Could in principle give the bidders information about what the other bidders have done at the point when they're called to play, right? Where this information could be true or could be false, right? Credibility says that the auctioneer mustn't want to lie about the information that she gives the bidders. Is there a static, credible, optimal auction? And it turns out that there is one, which I'd like to describe to you. So here is a credible strategy-proof optimal auction. What we're going to do is we're just going to keep track of the types of each bidder that are consistent with their previous actions. So it's the start of the game. All of the red bidders types are here. All of the blue bidders types are here. What I do is I set an optimal reserve, right, in the usual Meyerson way. Then I call up the red bidder and I say, hey, red, you're up to play. Will you bid the reserve? And red says yes. Then I call up bidder 2 and I say, hey, blue, you're up. Red's bid the reserve. Will you bid the reserve? And 2 says, sure. Then I call up red and I say, okay, red, blue's just matched your bid. Will you increase your bid by epsilon? And red says, sure. And I call up bidder 2, blue, and he says, sure. And we go up and up and up and up. Eventually, I ask bidder 2 to increase his bid, and bidder 2 says, no, I quit. Now, 2's not going to win. Red will win, and this is red's payment. Red's payment is the last bid that he placed. It turns out that this protocol, it's strategy-proof. I think we can all see it's strategy-proof. It's also credible. Why is it credible? In particular, at this point, the auctioneer can safely deviate. The auctioneer can, in principle, exaggerate bidder 2's type by increasing one's price by epsilon and asking him to pay more. Why doesn't he want to do this? Well, the answer is essentially, if you raise one's price, he might quit as well. So let's think about that. If you raise one's price, that's the probability that one's type is exactly equal to his last bid. If his type is exactly equal to his last bid, he quits, so you lose B1. On the other hand, that over there is the probability that one's type is strictly above his last bid, in which case, by exaggerating 2's type, you've increased your profits by epsilon. But this looks familiar. In particular, divide through by the probability mass function, and what you get is the virtual value at B1, right? That object in brackets is just the virtual value at B1. We're above the optimal reserve, so this object is positive, so the whole expression is negative. So you don't want to exaggerate bidder 2's bid. So it turns out that one interpretation of virtual values are that they are exactly the expected loss from shill bidding at a particular value in an ascending auction. Now, of course, this is actually not a proof. The real proof has to deal with a number of other deviations which are a little bit more subtle, but this is the one which I assume we all first worry about. It turns out you don't need to worry about these. So in essence, what the ascending auction does is by hiding information about the winning bidder's type, it makes it dangerous for the auctioneer to exaggerate the other bidder's type. In particular, the winning bidder reveals at each point in the auction no more than the fact that his type is at least high enough to win based on everything that the auctioneer knows so far. Now, that fills in the last corner of the triangle. There is a strategy-proof credible optimal auction. Result 2 in the paper is that this is the only one. So of all the extensive game forms you could select from, there is in fact a unique protocol that is both credible and strategy-proof. And you can write this out formally, but essentially that protocol is an ascending auction. So what this suggests, therefore, is a kind of auction trilemma. Here are 3 properties which you might find desirable. You might want to run a static auction because it's logistically easy. You might want to run a strategy-proof auction for all the reasons that we usually like strategy-proofness. You might want to run a credible auction. Their intersection is empty, But if you pick 2 out of 3 properties, you can have 2 out of 3. And picking 2 out of 3, in fact, entirely pins down the rules of one of the standard auction formats. Cool. So clearly, this is a special case of a more general framework. You could generalize this a little bit beyond private value auctions for a single unit. And some of those extensions are explored a little bit in the paper, but there's a lot of work to be done. But that's essentially where we're at. Thank you so much for your time. Peter?
So many years ago, the New York Board of Education conducted German auctions that suffered from what's called the magic number problem. And they were first price auctions where they opened up the envelope and awarded the project to the best bid. But the problem was corruption between the auctioneer and one of the first participants. And the first price auction suffers from that. So in particular, if you have, and this is, so if the auctioneer has a relationship with one of the participants, then they can
Absolutely.
a magic number that, and if they've got a cost that's less than the magic number, then they can bid just.
So you've just outlined exactly the next paper that we're trying hard to think about, which is coalitional deviations that involve not just the auctioneer, but potentially cooperation with the bidders. That's absolutely important. That's not captured by this framework, and clearly is an important venue for future work. Yeah? Yeah?
So you mentioned that, so I see why the proof that you gave, it's nice to assume regularity. You mentioned that you relaxed it in the paper.
Right.
Is there like an interesting technical barrier to relaxing it?
Oh, no, it's not difficult to relax regularity. In essence, what you do in an ascending auction is you commit to skip the bid ahead. If the bid ever hits 100 and we're meant to iron all the values between 100 and 150, in the ascending auction you say, once the clock hits 100, I'll skip it all the way to 150. And that, it turns out, is also credible. Jason?
I missed your argument for why the first price was the only static credible mechanism a little bit, and actually just why is the all pay not?
Oh, no, it's, to be clear, the all pay is credible. The first price uniqueness is driven by the winner paying assumption. There's a larger class of auctions which we call twin bid auctions, if you allow losers to pay money, of which the first price auction is the unique one in which the losers don't pay money. But yes, you're absolutely right. That proof relies on the fact that only winners pay. Otherwise, there is a large and, I think, interesting class. Cool. Eric?
In the ascending auction proof, what happens if the auctioneer calls me up and says, oh, the other blue bid 11, will you bid 12? I say no, so I drop out. That's the thing you're worried about, it's above the reserve price. And then the auctioneer calls me up and says, oh, something fell through with the
Right.
bid, how about?
Right, so this is, no, but this is, yes, this does happen too. So these are,
How is that outside,
so it's outside the model because the auctioneer in our world, in our very simple world, can say, if you're out, and I'm not going to call you back. So it's not a safe deviation to call someone back. But absolutely, like, I worry about this in the world.
That's part of what they've committed to in your
Yes.
your S0 game thing.
Yes, yes. They've said ahead of time, if you quit, you're out of the game. And so calling them back is getting called.
Violate, yeah.
Last question.
Cool?
So in your definition of the innocent explanation, the bidder doesn't consider how likely that's
Oh, yes. So in this sense, we're trying to hew very close to standard incentive compatibility. Standard incentive compatibility says you get to pretend to be any type with no restrictions about the likeliness of that type. And similarly here, we're letting the auctioneer pretend the other bidders have any types without any restrictions as to probability. And absolutely, that's a weakness both of this definition and the standard definition of incentive compatibility, that they don't allow us to penalize unlikely messages.
All right, let's thank Shengwu again.
Thank you so much.